current limiting resistors. Let's see why we need them and how to use them. First of all, here's a circuit that's working fairly well, and we can see the potentials on this circuit. At ground level we have 0 volts. At voltage source level we have 9 volts to act as a 9 volt battery, and at diode level we get 1.75 volts. So why do we need the resistor for the LED? Can't we do without? Well, first of all, this simulator cannot do without. We could simulate a circuit with a single ohm resistance, and let's see what happens then. So that would be the circuit without a resistor. We can see that the amperage has gone up quite a bit. It's 6.3 amps. Now 6.3 amps is quite a lot of amps for us, and we should limit that amperage. For a simple small light emitting diode, the amperage should be in milliamps. For this diode I have specified it should be 20 milliamps. And if it goes above that, it burns a bit brighter, but it'll fail quite quickly. Now it depends on the diode and the voltage source and the current capabilities of the voltage source, but it's generally a good idea to have a current limiting resistor between the voltage source and the diode, or whatever you are using in the circuit. So let's see, what sort of resistor should we have in here? Well, in the simulator we can just start and experiment with the resistor values. We can try different values until we get about 20 milliamps over here. So instead of 1 ohm, let's try 10 ohms. That should result in 0.63 amps or 630 milliamps. Close enough. 10 times better. Let's see, let's add a little bit more value to it. 100 ohm resistor. We already have 70 milliamps, which is about 2.5 times more than we need. 3.5 times? Yeah. So let's say 300 milliamps. We're close. 400? Nah, not quite. And let's try 350. And it's quite good. 20.4 milliamps instead of 20 milliamps, and that should work for this diode well. We have the current limited to the maximum current that is meant for this diode. We can try to tweak it a little bit from 350 to, let's say, 360 maybe. That's a little bit too much, so 356 maybe. Getting closer. 355, 4, other way. 5.8 maybe. Yay. And we've reached the 20 milliamps for this diode. So that's with experimenting with the resistor values, but let's try and calculate the values. Now I haven't made a proper custom diode over here, which I should do. Let's see. Okay. So I'm not going to do that over here, but as a generic red LED, it should have the forward voltage of 2 volts, which is about what we've got here, and 20 milliamps. So let's use these values to calculate the resistor size. And I have pre-made the calculation over here as well. So if the source voltage is 9 volts and the LED needs 2 volts for the forward voltage and 20 milliamps for the current, forward current, then we can use Ohm's law and Kirchhoff's voltage and amperage laws to calculate the resistor values, or in this case just the resistor value. So the Ohm's law says that resistance is equal to voltage divided with amperage on the component we are calculating it. So in this case we are calculating the resistance of the resistor, so we are dividing VR with IR, the voltage on resistor, with the amperage going through the resistor. Now we don't know the values from here, from our input info, so we have to calculate the VR and IR values. VR, or the voltage drop on the resistor, equals the voltage from the voltage source and the voltage drop from the LED. So if we get 9 volts over here and we want to get 2 volts over here, then that means that 9 minus 2 equals 7 volts on the resistor. We have to get 7 volts on the resistor to get 2 volts voltage drop on the diode. So that makes 7 volts on the resistor. So that's how we get the VR. This is called Kirchhoff's voltage law, which says that if we have the closed circuit, then the sum of the voltage sources voltage equals to the sum of the voltage drops in that circuit. Secondly, Kirchhoff's amperage, or the current law, says that if we don't have any dividing points in this circuit anywhere for the current to divide into 2 different directions, then the current stays the same in that circuit. So if we have 20 milliamps over here and the current doesn't divide between those 2 points, then we get 20 milliamps over here and over here and over here. So since we are targeting 20 milliamps through the LED, then we can use the same target value on the resistor. So now that we have the VR and IR values, we can place them into the equation and calculate the proper resistor value. So that's 20 volts over 20 milliamps or 20 volts over 0.02 amps, and that equals 350 ohms. Now if we look into the resistor standard values, then we don't have 350 ohm resistors. The closest are 360 ohms, 330 ohms, and 390 ohms, and 300 ohms. So, which one should we use? If we use, well, let me just write those down for you. We get 300 ohms, we get 330 ohms, we get 360, and we get 390 ohms. The closest to the 350 is 360 ohms, so that should be a no-brainer over here. And in our case, it would work just fine. 360 ohms, all of these resistors are with a tolerance of 10%, or wait, 5%. Up and down the value we can read from here. So actually the 360 ohm value could drop below 350 ohms. So that means that if we have a critical case that where the amperage shouldn't exceed the target value, we couldn't use just the 360 ohm resistor. We would have to use 390 ohm resistor or some resistance that is adjustable to the correct value. In our case, though, it really doesn't matter that much. If we exceed the target value amperage a little bit, let's say 10%, then the LED just glows a bit brighter and has a bit shorter life span, but that's all. And vice versa, if we use a larger than target value resistor, then the LED glows a bit darker but a bit longer. That is it. And we could easily use the 300 and 330 ohm resistors if we don't care about the life expectancy of the diode that much. It will burn out sooner, but it'll glow a bit brighter. That's all. And there's another thing we should take in account. It's the power that the resistor uses, and for the power we should use the equation power P R, I'm not going to use the equation this time, equals IR times VR. So in our case that would be 20 milliamps times 7 volts, which equals to 140 milliwatts if we get to use the 350 ohm resistance. And that is just the lowest value for the resistance. We could always use higher value, higher power capable resistors. And so that would be it for the current limiting resistor.